Okay, so today our mathematician spotlight is Pamela Harris. She's an assistant professor at Williams College. Before that, she was a postdoc at West Point, the United States Military Academy. And she studies algebraic combinatorics and representation theory. So here's an example of one of the things that she studies. So she studies like the intersection of algebra and combinatorics. So an example is visibility problems. So have you ever been driving along and there's an orchard on one side of the road, and you look, and as you're going along, the trees sort of like line up and then unline up, like zoop, zoop, zoop. Have you seen it? It's really cool, right? Like if you guys were all in precise rows, I could sort of go zoop, 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 and see all of you? Yeah. So you might ask, suppose you're at the corner, like you cut down one of the trees and you stand there in its place. Don't worry, you'll put it back soon. And you wonder, like, which of the trees can you see? So for instance, you can see these two trees that are next to you, but this one blocks all the ones behind it. So these ones you can't see. And this one you can see, but it blocks all the ones behind it. So you can't see that. And then on the diagonal, this one you can see, but it blocks all the ones behind it. Kind of like if you guys were in rows and I went like this, I wouldn't be able to see Charlie because, you know, he's blocked by everyone in front, right? So that's the idea. These red points are blocked. So, and also like this one you can see, but this one you can't see. This one you can see, but this one you can't see because it's blocked along this line. And so on. So you can figure out that along this whole second row of trees, you can see all of them. Same thing going up. But then you might wonder, how about this one? Well, 1, 2, 1, 2, 3, you can see this one. Same for this one. How about this one? 1, 2, 3, 1, 2, 3, 4, you can see this one. Okay, so you might wonder if we had an entire plane full of these things instead of just a 5x5 grid, how many could you see? So what proportion of trees can you see? It's equivalent to asking if you just randomly pick two positive numbers, positive whole numbers, what's the probability that they're relatively prime, that they don't have any common factors? It's the same problem. And it turns out, well, you might think the answer should be something like 1/2, because this is just a bunch of squares. But it turns out the answer is 6 over pi squared, which is about 61%. Pi? Where did pi come from? So that's a pretty cool problem. Pam didn't prove this, so this was already done before, probably before we were born. But she thinks about it in other contexts. So for example, suppose that instead of looking in a straight line, because straight is overrated, suppose that you looked in a parabola. So you're looking, and how about the parabola y equals x squared? Well, it would go through the point 1, 1. Oh, the point 1, 1, and then it would go through the point 2, 4. So this point would block this point, for example. So you might wonder if you're looking in the shape of parabolas. Parabolas are something that, for example, West Point cares about a lot. Which points are blocked? And so she's proved things about that. So, yeah, pretty neat. All right. So, today we'll do our first of 3 big theorems. So the last part of this class, we'll do 3 big theorems: Green's theorem, Stokes' theorem, Gauss's theorem, or Divergence theorem. And all of them are along the same theme. They're all generalizations of the Fundamental Theorem of Calculus. That if you want to know about something on a region or an interval, you want to care about something else on the boundary of that region. So that's the theme of the Fundamental Theorem of Calculus and all of these theorems. So today we'll do integrating. We'll show that integrating a vector field over a curve is the same as integrating some scalar actually valued function over a region. So these are the same, and that's by Green's theorem. So if you have some vector field that's doing something. Who knows what it is? It's doing something like wind. And then you have some curve oriented in some way. And you want to integrate the vector field over the curve. Green's theorem says it's the same as integrating some scalar function, a related scalar function that we'll define, over the region inside, that region. So that's what it's going to say. Before we do that, we'll do a couple of examples of integrating over vector fields. So the plan is, the first example, the point will be understanding new notation for integrating vector fields. There's a new notation that is more convenient in some contexts. So we'll do that. And then the second example will be tedious to compute, and then Green's theorem will help us. So we'll do it directly first, and then we'll bring in Green's theorem and show that it's much easier to do with Green's theorem. So that's the goal. Okay, so let's do our first example. 1, if you will. So let's integrate, find the vector line integral over C of yz dx plus xz dy plus xy dz over the curve C which is parameterized by x of t equals t squared t cubed, where t goes from 0 to 2. Okay, that's the goal. So, okay, this part I understand. My curve looks like t comma t squared comma t cubed, so it's doing something, some sort of little spirally thing for 2 seconds. That I understand. But this, what is this? This we have not seen. So you might wonder, what on earth is this? So let's try to figure out what it could mean and then see why it's helpful. So the integral over C of yz dx plus xz dy plus xy dz, you might notice it's something times something plus something times something plus something times something. So anytime you see something of that form, you think, yeah, dot product. Dot product, yeah, it's a product of something. So this is the integral over C of yz, xz, xy, dot product, dx, dy, dz. Okay, so here's what you can think of. This is our vector field. So this is our f of x, y, z. That's our vector field. And then this dx, dy, dz is just our ds. It's just a little piece of infinitesimal line integral, little infinitesimal arc length vector along the curve. So for instance, this here, if here was dx, and here's dy, and then here coming out of the board is dz, then that's just this little tiny vector in the direction of the curve. So if it was just dx, dy, then ds would be the diagonal. So I can't draw it into the third dimension. But that's the idea. This is a little infinitesimal piece of direction in the direction that you're going along the curve. Okay, so the long and short of that is that it just means the same thing that we've been doing before. It's f of x, y, z dot ds. So why is this notation kind of helpful? Well, it says if you want to measure how much the function is going in the same or the opposite direction as your curve, right? You want to know how much the vector field is helping or hurting you as you go along your canoeing path of a curve. Well, it depends how much. How much is the vector field helping you in the x direction, plus how much is it helping you in the y direction, plus how much is it helping you in the z direction. So that's each of these parts here together, and we add them up. So let's try this. So let's rewrite this in an order that we can actually integrate. So we know if you want to plug everything in terms of t so that we can actually integrate this thing, we know what x, y, and z are in terms of t. They're t squared, and t cubed. So we know x is t, y is t squared, and z is t cubed. And now, so that's good for all these parts, x, y, and z. But how about dx, dy, and dz? Let's figure out what those are. So to do that, we can just take the derivative of each of these. So the derivative of x is dx, the derivative of t is dt. So take the derivative of both sides. Here, same idea, dy, take the derivative of this guy, 2t times the derivative of the inside dt. And for z, same, dz is 3t squared times the derivative of the inside dt. So this is the infinitesimal way that x, y, and z are changing if you change t a little bit. So if we were to change t a little bit, x would just move however much t is moving, y, the amount we would move depends on what time it is, and z, the amount it would move also depends on what time it is. Yeah. Okay, let's try setting it up and computing it. So this is, okay, y times z. I know y is t squared, and z is t cubed, and dx is dt. So going along, this is my x, this is my y, and this is my dz. Okay, then I have x, z, dy. So x is t, y, z is t cubed, and dy is 2t dt. So this was x, z, and dy. And then finally, we have x, y, dz. So x is t, y is t squared, and dz is 3t squared dt. So this is x, y, and dz. So I just rewrote everything in terms of t, and then I want to integrate it for whichever t's I'm interested in, which is t goes from 0 to 2. Okay, now let's just do it. So we could notice that here at the beginning we have t to the 5th. This is just t to the 5th dt. This is, again, t to the 5th, but it's two of them. 2t to the 5th. Okay. Good. Okay, yeah, question?
Could you also break up the integrals so that you have something from 0 to 2 dx, 0 to 4 dy, and 0 to 8 dz, x and y in terms of whatever variable you pick?
Oh.
Using the relationship that x equals t squared equals y and t.
So break up these three pieces?
Right. And then integrate dy, dx, dz while turning the other variables into some.
Oh, yeah, sure. Absolutely, yeah. Good. Okay. Nice. Okay. Okay, so that was a nice integral, and the purpose of that was to check out this new notation, which is sometimes helpful and makes things easier sometimes. Okay. For the second example, we'll set up something that is tough to do, but will be easier when we apply Green's theorem. So here's the goal. Compute the line integral of the vector field 2x squared minus 3y squared, 2x plus 3y squared, over the curve C, consisting of the following three pieces. So first, we start at -2, 0. Then we go to 2, 0. So that's the first part of C. We'll call that C1. Then we go from 2, 0 up to 2, 2. We'll call that C2. And finally, we go from 2, 2 back to -2, 0. We'll call that C3. So that's the curve C. It does all three of those parts. So let's try this. So the integral over C of f dot t ds is just the sum of the integrals over the three parts. Yeah, we'll just integrate them over the three parts and we'll add them up. That's really the only way to do it because it's different on the three parts. So let's do this. So we'll do the first parts by cleverness. So trying our clever trick of when things are horizontal or vertical, we can sometimes simplify our lives. And then for C3, we'll use the equation. that always works. We could use the equation for all three of the parts, but for fun, we'll do the first two parts with cleverness. So on C1, let's see if we can figure out what these parts are. So F, well, let's see. On C1, it's along the x-axis, so y is always 0. So y is always 0. So our vector field is, well, everywhere we see a y, we can plug in 0. So it's just 2x squared, comma, 2x. So let's look at what this looks like. So 2x squared, that is always positive, so it's always moving to the right. And then 2x, that's negative when we're on the left and positive when we're on the right. So it looks like it should go something like this, this, something like that, approximately. So maybe we would expect a positive answer because it looks like the vector field is generally pointing the same way as C1. So expect answer to be positive. Okay. Also, how about our unit tangent vector? So this is just the way that we're going. It's a unit tangent vector in the direction that we're going. And the direction we're going is to the right. So our unit tangent vector in that direction should just be 1, 0. So t is 1, 0. And also, ds is like a little arc length parameter in the direction that we're going. But we're always going in the x direction. So ds should be dx. So these are because we're always moving in the positive x direction. If we were moving in the negative x direction, ds would be negative dx, going the other way. Yeah?
Does the fact that we're at the line of y equals 0 have any impact on the unit tangent vector?
It does not matter that we're along the line y equals 0 for the unit tangent vector. It's just the fact that we're going to the right. It just tells you the direction that you're going. Yeah. Okay, so let's try to set this up. So the integral over C1 of f dot t ds is, okay, well, f is 2x squared 2x. Let's put that in. 2x squared, comma 2x, dot our unit tangent vector, which is 1, 0, times ds, which is dx. And let's see, we have to figure out which x's we're interested in. X goes from negative 2 up to 2. So x goes from negative 2 up to 2. So let's compute this. X goes from negative 2 to 2 of, if we take this dot product, 2x squared times 1 is 2x squared, plus 2x times 0 is 0. Okay, so dx. So if we integrate this, we get 2/3 x cubed from negative 2 to 2, which comes out to 32 over 3. Which, as we thought, is positive. Okay. Okay, let's try C2. So C2, we can also be a bit clever because it's vertical. So along C2, x is always 2. So f is, well, in this vector field, everywhere we see an x, we can just put a 2. So 2 times 2 squared is 8. So we get 8 minus 3y squared. 2 times 2 is 4, so 4 plus 3y squared. And then how about our unit tangent vector? We're always going up, always going in the positive y direction. So 0, 1. And similarly, for our ds, we're always just going in the positive y direction. So ds is just dy. So these are both because we're moving in the positive y direction. Yeah. So this is an example of what you're asking about. Like, what does it matter where you are that your vector is 0, 1 or 1, 0? Nope, it could be anywhere, just the fact that we're going in the y direction. Yeah. So let's set this up. So the integral over C2 of f dot t ds is the integral of f, which is 8 minus 3y squared, 4 plus 3y squared, dot t, our direction vector, so 0, 1, times ds, which is dy. And we're interested in y's from 0 to 2. So let's compute this. Something times 0 is 0, plus 4 plus 3y squared times 1 is 4 plus 3y squared. And we want to go from 0 to 2. So this you can compute. Whatever it is, 4y plus y cubed from 0 to 2, which comes out to 16. Okay. And I didn't draw a picture of what it looks like, but along this 8 minus 3y squared when y is 0, this is 8. This thing is always positive, so at the beginning, the vector field looks like this. And then when y is 2, this is 8 minus 12, which is negative 4, and this is still positive. So it goes something like that. So the wind changes direction as you go along your canoe trip, but it's always kind of pushing you forward. So we are not surprised that this comes out positive. Yeah, questions or ideas? Are you ready for C3? C3, we're going to have to use the formula. So for C3, we'll use the equation or the formula. So the integral over C of f dot t ds is the integral from t equals wherever you care about at the beginning to t equals whatever you care about at the end of f of x of t, your parameterization, dot x prime of t, your tangent vector, dt, or your velocity vector, dt. So we want to, in order to integrate along C3, we're going to have to set up this thing. So let's do the parts. So the first thing we'll need is x of t, our parameterization. So let's figure out what x of t should be. So x of t just says, what is your x value and what is your y value? This x isn't the same as the x coordinate, but it is standard to use this notation. So what is your x of t and what is your y of t? So we're going to start at 2, 2, and we're going to go to negative 2, 0. So this is something we did at the very beginning of the course, parameterizing lines. So you do where you start. So we start at 2, 2. Plus what direction you're going. So let's compute what this vector is. This vector is negative 4, negative 2. So we're going in the direction negative 4, negative 2. So if we multiply that by t, that'll allow us to go anywhere on the line that connects these 2 points. So for example, if t equals 0, this whole part goes away, and we get the point 2, 2. If t equals 1, then we add just one of this vector, so we get negative 2, 0. So that takes us from 2, 2 to negative 2, 0. So t equals 0, t equals 0.1, 0.2, here t equals a half, all the way up to 1. So the t's we want are from 0 to 1. You could also have, if you wanted to, you could have said, I want this vector to be negative 2, 1, just half as big, but then you'd have to take your t all the way to 2, because it takes you 2 seconds to go from one point to the other. And everything would work out okay. Okay, so this is our x of t. I'll write this in more compact form as 2 minus 4t, 2 minus 2t. So that's our x of t. And then we'll also need, that is good for here, we'll also need our direction vector, our velocity vector. So x prime of t is just the derivative of the first thing. So that's negative 4, and the derivative of the second thing, which is negative 2. And this one is our position, and the second one is our velocity. And it shouldn't be too surprising that our velocity is vector is negative 4, negative 2, because that's where we're going. We're going from 2, 2 to negative 2, 0 along negative 4, negative 2. Okay, so let's set this up then. We'll also need f of x of t. So f of x of t is, well, what is f? F is 2x squared minus 3y squared. I'll write that down. 2x squared minus 3y squared, so I know where I'm going. So it's 2 times x to minus 4t squared minus 3y squared. So 3 times 2 minus 2t squared, comma, 2x plus 3y squared. 2x plus 3y squared. 2 times 2 minus 4t plus 3 times 2 minus 2t squared. Okay, what a mess of a vector field. But the point is that this tells you no matter what time it is, for example, if the time is 11:57, it tells you what your vector field is. What time is it? What's your vector field? So it tells you whatever time it is along the curve, how your vector is pointing. Okay, so we want to compute the integral of f of x of t dot x prime of t dt from t equals 0 up to t equals 1. So let's plug it in. So this is from t equals 0 to t equals 1 of this whole thing. So I'm not going to write it out again. I'll just say it's this, and it goes in here. That's that whole thing. Okay? Dot x prime of t, which is -4, -2, dt. So I'll omit the calculation there. But that if we go from, that's going from t equals 0 to t equals 1 of this whole thing times -4 plus this whole thing times -2. So it's a bunch of things squared in linear terms and constant terms. And when you multiply it all out and simplify, you get -104t squared plus 96t minus 16 dt. And this you can do. And if you were to do it, you would find that it was, I did it, it was -8/3. So it tells you that along C3, the vector field is kind of working against you, just a little bit. So we figured out what the vector line integral was over each of the 3 curves, and now we'll add them up. So the vector line integral over C of f dot t ds is the integral over C1 plus the same integral over C2 plus the same integral over C3, which we figured out were 32/3, 16, and -8/3. And if you add these things up, you get 24. So it tells you that the vector field is helping us go along our curve to the tune of 24. Yeah. Questions or ideas? Okay, so one question might be, wow, that was so complicated. Isn't there a better way? I hope there's a better way. And the answer is that the better way is Green's theorem. So this took us 1, 2, 3, 4 pieces of chalkboard, quite a lot of computations, and we had to do it in 3 parts, 1 for C1, 1 for C2, 1 for C3. There wasn't any way around that because our curve had like 3 different parts that were different. But Green's theorem will allow us to do it in one line and all at once. Okay. So Green's theorem is about vector fields in the plane. So just 2-dimensional vector fields. So let me make sure I get all the words the way that they're supposed to be. Right. Okay, so for vector field, f, which is p comma q, so those are both probably functions of x and y. So we can draw our vector field so that we have something to think about. So here's our vector field. Who knows what it's doing? It's doing something. There's our vector field, where P and Q have continuous partial derivatives throughout a region D in the plane. So D stands for domain. So you can think of our domain as being like that triangle over there, or maybe just some blob region. So here's our domain D. In the xy plane, whose boundary, which is denoted boundary of D. This is the same symbol as del that we use for partial derivative, but here it's now used for boundary. Boundary of D consists of simple closed curves. So a simple curve is a curve that doesn't intersect itself. So for example, this is a simple curve. Our triangle was a simple curve, but something like this that does intersect itself, that's not simple because it intersects itself. A closed curve is a curve that goes around, does whatever it wants, and then closes up. So this is closed. This one is actually also closed, but something like this is not closed because it doesn't close up. You go around it and you don't get back to where you start. So that's what simple and closed mean. We have that the line integral over the boundary of D of the vector field dot ds, so that's also written in our new notation as p dx plus q dy. So that's the line integral around this curve of this vector field is equal to the double integral over the interior, the domain D on the inside, of q, the partial derivative with respect to q with, partial derivative of q with respect to x minus the partial derivative of p with respect to y dA. So we want to integrate this related function, q sub x minus p sub y, over this domain. And it says that they're equal. As long as the orientation, so we want to make sure the sign is correct. So as long as the boundary is oriented, so it has a direction such that D is on the left when walking around it. So in the plane, all this means is that it's oriented counterclockwise. But you can imagine that you put your right hand in your pocket. That's not usually where your right hand goes. Usually you're using it for the right hand rule, but for this, put your right hand in your pocket, and you put your left hand out like this, and you walk along the curve. And you want to make sure that your arm is over the domain all the time. So in the plane, that's just counterclockwise, but I'll define it this way so that you get used to thinking about putting your left arm out, because in the future, we'll orient things in 3 space where counterclockwise isn't well defined. So you imagine you have your person walking along with their left arm, and their left arm is always over the domain. Okay, then these things are equal. So let's try it for our function. So what we'll do for the rest of class is we'll try it on our triangle thing and see that it works, and then we'll talk about why it's true, and maybe do one more example of it. So let's apply this. So apply it to the previous example. So let's check. Our vector field was PQ, which was 2x squared minus 3y squared, comma 2x plus 3y squared. And we have to, it has to have continuous partial derivatives throughout the region of the triangle. What do you think? Does it have continuous partial derivatives throughout the triangle? Yeah, it actually has continuous partial derivatives anywhere. Nothing goes wrong anywhere. It's a polynomial. So it has continuous partial derivatives, yay, throughout the region D in the plane, whose boundary consists of simple closed curves. So in this case, the boundary is a triangle. It's simple, doesn't intersect itself, and it's closed. It ends where it starts. So simple closed curves, yay. And let's just check the orientation first. The triangle is oriented such that D is on the left. Is that the case? If you walk along here, would your left arm be over the region in the middle? Yeah, okay. So this here is our D then, and it's on the left. So it seems like those are all satisfied. And so we can say that the integral over C of p dx plus q dy is just the double integral over the domain of qx minus py dA. Okay, so let's set this up. Partial derivative of q with respect to x is just 2 minus partial derivative of p with respect to y is negative 6y. So 2 minus negative 6y is 2 plus 6y. And now I want to set up my integral. I'll redraw it over here. So this is 0, x is 2, x is negative 2. Here y is 2. Let's integrate. We could do either order. Let's do y on the outside and x on the inside. So that's dx, dy. So my y's are going to go from 0 up to 2. And for the x's, let's see. This line here, I go from x equals whatever it is on this pink line over to whatever x is on this purple line. On this purple line, it's 2. So x at the top is 2. And then this line is like y equals y-intercept of 1 plus half x. So if you solve for x, I think you get x equals 2y minus 2. So on this pink line, x is 2y minus 2. Okay, so I suppose you've set up double integrals a bunch of times. And you can see that this one is not so hard. Yeah, if I had given this to you, problem number 1 on the test, you would have opened the test and you would have been like, yes, I got this. So this you can do. And in this, there's this line, then there's this line, and then the last line is that the answer is 24. So it makes it much easier. We did it all in one fell swoop by integrating over the domain and the inside instead of integrating over each of the boundary pieces. Yeah. Questions or ideas? So one question you might ask is, why on earth does this work? Right? Like, this is crazy. What is the idea here? So that's what we'll have to talk about. Okay. So the idea of Green's theorem. Okay. So you have some region here. This is your curve, C. It's oriented in the proper orientation. And you are very interested in the line integral over C of f dot ds. Okay, you're very interested in that. Okay, you know how sometimes you can make the problem more complicated and then it gets simpler? We're going to make it more complicated first. So what we're going to do is, instead of just integrating over C, we're going to integrate over. We're going to break it up into a bunch of little boxes. These could be infinitely small, but so that you can see them, I'm making them big. Instead of that, we're going to integrate over all of these lines, so all the green lines and the white lines. So suppose you took the line integral over C. So suppose we took the line integral over C plus all of these ones, so we'll call them all CI, all the line integrals on the inside of f dot ds. Okay, well, check this out. So we're going to have to parameterize each of these little rectangles or squares separately. Yeah? And we'll compute the line integral of f along, say, this, and this, and this, and this. And then, over here in the next triangle, we'll do the line integral here, 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 and here. The upshot of it is that whatever you got for the line integral of this left square going up, it's equal and opposite to the line integral along the same edge in this purple square going down. So actually, all the line integrals on the inside, all the green lines, cancel. Because each one, let's say this one, it's got one on the left and one on the right that are equal and opposite. Same thing up here. One on the top and one on the bottom. They're equal and opposite. So they all cancel each other out. So these are actually equal. So by throwing in all the extra line integrals over these little bits, it doesn't change anything. Okay, so now the line integral over each of these little guys, well, it's just saying how the vector field is moving. So if the vector field were going counterclockwise in this little box, we'd get a positive number. And if it were going counterclockwise in this little box, we'd get a negative number. So that's just like calculating the curl in each box. So the idea is that you're calculating the curl in each box. So this is the same as, for every little box, calculating the curl of f. You're just calculating whether the thing is going counterclockwise or whether the thing is going clockwise. Let's think about curl of f. So if f is a vector field of the form p and q, where these are just functions of x and y, we can think of this as being p, q, 0. It's a vector field in the plane. No z components. Throw in a 0 for z, no problem. If you compute the curl of f, well, it's I, j, k, partial with respect to x, partial with respect to y, partial with respect to z of p, q, 0. We get, let's see, the first component is derivative of 0 minus qz. The next one is negative derivative of 0 plus, minus, now it's plus pz. And the last component is partial with respect to x of q minus partial with respect to y of p. So qx minus py. But this is just functions of x and y, these p and q, because it's all happening in the plane. So derivative of q with respect to z and p with respect to z, those are both 0. So this is just 0, 0, qx minus py, which we know, right? If you have a vector field in the plane, at each point it's either spinning counterclockwise or spinning clockwise, so your curl vector either points up or points down. So it's purely z component. So that's the idea of why this comes out to double integral over d of the curl of f. The curl of f is essentially just qx minus py. That's how much the thing is moving counterclockwise or clockwise. Yeah. So that's the idea, is that you break this up into little pieces, and then you think of computing the curl at a point inside these, and when the boxes get really small, it's just an area integral. Yeah. Okay. So I'll mention that this is a generalization of the Fundamental Theorem of Calculus, and then we'll do one more example. So the Fundamental Theorem of Calculus says that if you have some function on an interval from a to b, and you want to take the integral from a to b of f of x dx, well, you find the antiderivative of f of x, let's call it big F, and you do f of b minus f of a. Yeah? So if this big F is the antiderivative of little f, I could just call this little f f prime of x. So this function here is f prime of x. The Fundamental Theorem of Calculus says, oh, you're interested in knowing something about a derivative on an interior? So this is integral of a derivative on interior of the interval ab. Oh, you want to know something about the values of the function in here? Is that what you want? Oh, well, all you have to do is look at the function on the boundary of the interval. So it's kind of funny to think about the boundary of an interval, but the boundary of an interval is just 2 points, a and b. So, oh, you want to know something about the derivative on the inside? Well, that's the same as knowing about the function on the boundary. So the integral of the derivative of the inside is the same as the function, something about the function on the boundary. And that's the same thing over here. Green's theorem is saying you want to know something about the derivative of the function on the interior? Oh, well, you should look at the function itself on the boundary. So the fundamental theorem of calculus relates something one-dimensional to the boundary, which is zero-dimensional, because points are zero-dimensional. And Green's theorem relates the interior, which is two-dimensional, the region that we're integrating over, to the boundary, which is one-dimensional, just the curve. And also, we'll see Stokes' theorem, which is just taking Green's theorem and kind of pushing it into free space. The same idea. And then finally, Gauss's theorem, which is also called the divergence theorem, does the same thing, but we look at the interior, which is three-dimensional, and relate it to the value of the function on the boundary, which will now be a two-dimensional surface. So you think about this as being like thinking about balloons. You have some value of the derivative on the air inside the balloon is related to the value of a function on the surface of the balloon. So that's the idea, and these are the theorems that we'll do in the last part of the course. Okay, so relating it to just one more thing, suppose we want to compute the line integral over the boundary of a half disk of our favorite vector field. So compute the line integral over C of negative y dx plus x dy over the curve consisting of this part kind of going the wrong way. The curve consisting of that, a D shape. So let's check that everything satisfies the constraints of Green's theorem. So our vector field is negative y comma x. It has continuous partial derivatives everywhere. All good. It bounds a region in the plane that whose boundary is simple closed curves. This D shape is simple and closed. Great. So this continuous partial derivative, simple closed curve. Yep. And oriented counterclockwise. No, not oriented counterclockwise. Okay, so we'll just have to change the sign. So the integral over C of f dot t ds is the same as the negative of the integral of negative C of f dot t ds. And negative C is counterclockwise because C was clockwise. So we'll do the negative of our integral. So we want to set up a double integral over this region, which we'll call D, which makes sense because it's a D shape, of q sub x minus p sub y dA. So let's do that. That's negative double integral over our domain, q sub x. Okay, this one is p, this one is q. Q's derivative of x with respect to x is 1 minus derivative of negative y with respect to y is negative 1. So 1 minus negative 1 is 1 plus 1 dA. So we're doing negative double integral over d of 2 dA. So that's negative 2 times the area of our domain. If it were the whole unit disk, it would have area pi. It's only half, so it has area pi over 2. So negative 2 times pi over 2 is negative pi. So in this case, we now didn't have to parameterize two different curves. So we're happy. We should check that it makes sense. Our vector field is our favorite vector field, negative y comma x. This is one of our favorite two. This one goes counterclockwise around things. So it's perpendicular to the thing on the straight part, and it goes in the opposite direction along the curved part. So we're not surprised that this came out negative. Yeah. All right. Thank you.